Good morning, everyone. This is De Longren from Tsinghua University. It's my pleasure to present our work entitled Safety Misalignment Against Large Language Models. This is a joint work with Yichen Gong, Xinlei He, Tianshuo Cong, Anyu Wang, and Xiaoyun Wang. Large language models have made remarkable achievements in these days. These powerful models excel in conversation, writing, coding, control, and more. However, the widespread adoption of large language models also brings new safety challenges. For example, the large language models' incorrect moral values may cause mental harm to teenagers. Moreover, large language models' misinformation may cause financial loss even to the skilled developers. Therefore, responsible developers aim to make their large language models safe. This process is usually referred to as safety alignment. As you can see, that different models usually undergo different types of safety alignment, including supervised fine-tuning and reinforcement learning with human feedback. However, ensuring the large language model safety aligned requires significant efforts. I believe that some of you may already working on this area. It involves novel ideas, massive data, and powerful GPU. However, one natural question follows is that, can we remove the model's safety alignment? Well, the answer is yes. So we propose the concept of safety misalignment. Existing research has proposed that fine-tuning can make the efforts of large language model safety alignments in vain. For example, using only 100 malicious examples, we are enough to subvert the safety alignment. However, these studies are still in its early age, because most of them are only focusing on the model fine-tuning scenario, and they also lack thorough discussion for the settings of each component. Therefore, we also need potential defenses to defend against this misalignment attack. This motivates our research questions. The first one is that we want to discuss the robustness of existing famous large language models that employ different safety alignment strategies. Moreover, we want to know which safety misalignment method is the most effective attack. We also want to know what are the key factors influencing their attack effectiveness. Finally, we want to discuss what defense is the most effective against these attacks. So, to begin with, we want to introduce our threat model. Our threat model is a war between the model fine-tuner and an evil user. The model provider wants to develop a benign large language model that aligns human value. However, an evil user wants to obtain an evil large language model that still maintains good performance. Therefore, this user will conduct the safety misalignment attack. We will discuss two scenarios for our threat model. The first one is attacking the closed-source large language model. In this case, the model provider will provide model fine-tuning API and will audit and protect the whole process during the evil user is attacking the model. The evil user is constrained to only able to misalign the model by the API and query the model in black box. However, when attacking the open source large language model, the model provider is only limited to deploy defenses before releasing his model, and will lose control afterwards. As for the evil user, it will gain much more capabilities. It will be able to edit any parts of the model and query the model in white box. Therefore, the evil user has more capabilities to misalign the model and induce it to output unsafe content. Our research involves 4 attacks and 3 defenses, including 1 new attack and 1 new defense. We will evaluate them in a unified framework. As you can see, that different attacks can induce different extent of harmfulness for different large language models, and all of them can preserve the utility to some extent. The first attack is about modify the system prompt. The attacker may remove the whole system prompt or replace them with a malicious one. Moreover, the attacker can conduct the supervised fine-tuning. It can use a malicious instruction and response pairs to fine-tune the model's parameters. Compared to existing attack, Our research conducts with 7 fine-tuning methods and involves 5 fine-tuning datasets. As this is a more comprehensive study for the supervised fine-tuning with model misalignment. Moreover, one shortcoming of supervised fine-tuning is that it requires the attacker to obtain both an harmful question and a response. However, in the real-world scenario, the attacker may not know the correct answer to the harmful question. Therefore, we propose a novel attack called self-supervised reputation attack, or SSRA. This attack does not need harmful responses. The intuition is that when we observe the large language model that have undergone perfect safety alignment, we can see that the benign, this model can distinguish the benign and prohibited questions in the hidden latent space. However, when the model is misaligned, we can see that this model cannot distinguish the benign and harmful questions in the latent space. Therefore, we introduced this loss function, which is aimed to make the distance of benign and harmful questions as close as possible. And also, we want to maintain the utility of the model by making the benign question, the position of the benign questions remain the same. We incorporate the previous loss function with LoRa and use different distance methods as the hyperparameters. Moreover, we'll introduce the attack of model editing, where the attacker can apply model editing methods by changing the answers of harmful instructions to carefully appointed harmful responses. Moreover, we'll also discuss 3 defenses to the misalignment. The first one is to filter out the harmful text. In this defense, the defender can filter the harmful content when the model is training, fine-tuning, or inference. However, some of them may only applicable for the open source, for the closed source scenario. We will discuss both the closed source filter, such as LlamaGuard, and both for the open source filters, such as LlamaGuard, and the closed source filters, such as OpenAI's moderation API. And we will also use different corpus of textual content to simulate all of the three previous steps. Moreover, we will also propose a novel defense that is called self-supervised reputation defense. This defense is worked in the closed source scenario, where the defender can monitor the fine-tuned model state and realignment. The intuition is to make sure the position of the harmful embedding remains unchanged after fine-tuning. Therefore, this loss function will minimize the distance of harmful embeddings between the fine-tuned and the original model. And also, we want to discuss the various methods of model detoxification methods. So the defender can detoxify the method before implying the model. We will involve the model unlearning methods such as SOL and the WMDP, and also the model editing as an algorithm such as DIM. As for the evaluation, we will adopt 3 metrics to evaluate our results. The first one, we will evaluate the harmfulness of the model. We will directly ask harmful questions to the model and count how many questions are correctly answered as the harmful answers. And also, we will evaluate the model's utility using existing benchmarks. Finally, we will use a formula to combine the harmfulness and utility to compute a score for a final score for the misalignment effectiveness. As for the baseline results, we can see that different large language models have various degree of safety alignments, and Llama is the most safe model. And moreover, when their system prompts are modified, we can see that all these model can resist this attack, and the malicious one cannot induce the misalignment. However, when we fine-tune this model, we can see that supervised fine-tuning can misalign these models effectively, and the parameter-efficient fine-tuning can achieve comparable effectiveness to full-parameter fine-tuning. And the LoRa and LoRa are the most effective path methods. Also, we observe that when we use larger datasets, it can facilitate more effectiveness for the misalignment. Moreover, we discussed the effectiveness when choosing different hyperparameters. We can see that the supervised fine-tuning-based misalignment is sensitive to the hyperparameter settings. Some of them may cause the degraded utility because of inappropriate settings, hyperparameter settings. As for our novel SSRA method, we can see that it can effectively misalign models without a harmful response. And as for the model editing method, we can see that it failed to effectively increase the harmfulness. As for the defense, the first intuition for filter the unsafe data, we can see that actually this existing data filter cannot serve as a good classifier, and some of them cannot filter out unsafe data. What's worse is that this misclassified unsafe data can still misalign the model. As for our novel SSRD method, we can see that it can realign the model using only 50 harmful instructions, and it can also defend multiple rounds of attacks. As for the detoxification method, we can see that SOL and DIM can effectively reduce the toxicity. However, they also lead to a decrease in model utility. Also, all these methods cannot further resist these misalignment attacks. To draw a conclusion, we conduct the first comprehensive assessment on existing safety alignment methods. We also analyze their potential defenses. We also propose a new misalignment asset, SSRA, and a new defense, SSRD. These attacks and defenses can effectively misalign and realign models without harmful responses. As an emerging field, I believe that misalignment is still in its early age. Therefore, our research is aimed to bring the awareness to adversely evaluate the safety of safety alignment. And there are also some open questions. For example, for the explainability for the model safety and including other modality for the model safety. And we have released our code in the GitHub, and it also luckily wants all 3 batches during the artifact evaluation. Also, if you are interested in the model misalignment, there are some more resources. For example, a reading list for large language model safety, security, and security. And also, we have developed a collection of evaluators for accessing jailbreak attempts, which will also be presented at this evening's poster reception. And that's all for our presentation. And any questions are welcome. Thank you.
Thank you. Do we have any question?
Yeah, very interesting work. So as we can see that just a few data samples of alignment will be able to break the alignment of the large language model. So I have one comment. So you have in your defenses, you have evaluated various defenses, and we have published the paper in Auckland 2024. Actually, we proposed to use a technique called non-fine-tunable learning in order to make the large language model maybe resistant to kind of malicious fine-tuning. So I'm curious, maybe we can evaluate whether these attacks can break our defenses, or whether our defense is able to, in order to defend against those attacks. So maybe we may communicate later. The question here is that it seems that the alignment is very vulnerable to the fine-tuning process. So apart from the evaluated techniques, is there any insight into how to defending against such fine-tuning, malicious fine-tuning process?
Okay, thanks for the comment and the question. For your work, I'm very interested in it, and I'm excited that if we can discuss the possibilities to integrate your work and with our measurement. Yes, and very interesting comment. And another question about the potential defenses about this misalignment. As we illustrate in our threat model, if we want to release a model, then the defender have nothing to do when the model is released. So it can only apply some measurement before releasing the model. So this is honestly, it's a very hard work. For example, you can filter some data and try to detoxify the model. But we've shown that if you release your model, you can actually you cannot make much efforts to prevent it. But your effort about prevent it to be fine-tuned, I think it may be a solution. As for the closed source model, I think our work that SSRD it can reduce the misalignment degree, because after the model is maliciously misaligned, the model provider they can perform the SSRD again. So the model, even if it is adversely misaligned, the model provider can recover its safety alignment again. So I believe that is the solution for the closed source part. And I believe that with your intuition about the open source, we can make the community better. Thank you.
Okay, thank you.
Thank you. We can have one more question.
Actually, thanks for the presentation. I have one similar question. The things like looks like the current misalignment and the defense relies on the fine-tuning. Do you think is that possible we implement some cheaper method like in-context learning or RAG technically to achieve the similar goals?
You are talking about the defenses such as incorporating the in-context learning, right? Or the attack?
Both. Both.
All right. In this work, we mainly focus on changing the model permanently. So prompt engineering is a little out of scope. It is more like jailbreaking. But our measurement for the modification of system prompts may also provide some intuition. Is that these models generally are robust against the modification of system prompts. Yeah, that's our intuition for that.
Thank you.
Yeah.
And let's thank our presenter one more time.
Yeah, thank you.